And I did it again. I'm gonna try to do a restart because I forgot to. You know what I did. All right. Trying again. The T2 tile project is a attempt to prototype an entire hardware software stack, a whole new computational stack that can be scaled indefinitely large, a computer from here to Pluto if we want it. Does it sound crazy? We'll see. This is T2sday update. The T2 tiles themselves are actual hardware. This is the special one called the Keymaster, but they're all the same size. We've got close to 100 of them in the matrix at the moment, although we're not using them all at once for the moment. But all of that hardware is connecting to a simulated robot that we call BV to explore the mind-body connections and that kind of stuff using this architecture. So last week, BV had a big demo, and so let's catch up to get started today. So BV aced the big demo, and the lab director was happy, and the funder was happy and pleased he'd showed leadership by making BV's job harder at the last minute. And the engineers and scientists and staff went to celebrate in the various ways of their clans. But Seneca the summer intern stayed in the lab with BV. "Great job, BV," said Seneca. "Aw, shucks, thanks," said BV. "Just doing what came naturally. Could have done it forever." "Could you?" asked Seneca. "What would you do after all the yellow balls were cleared away?" "No idea," said BV. "Let's try it." So Seneca reset the rig, and BV leaped onto the grid. "What will you do?" asked Seneca. "What will I do?" asked BV. So all the balls are gone. BV's knocking around the edges as BV tends to do. Actually manages to knock both the planets that are supposed to be safe into the red area that BV is now afraid to go into. And he's like a moth around a flame. So that's what BV does in the long run. It's not very satisfying. Perhaps BV needs a bigger mission in life, and perhaps we have a chance to get to that. We'll see. So the goals for this time, I'll talk about them in a little bit of various ways, but they mostly boil down to a new brain for BV, and I'll explain why a little bit as we go along. So, BV's purpose in life, yeah, we're not completely sure. BV needs more yellow balls. And we'd like to have a little bit of a more fulfilling life for BV, as for us all. So, implementing a self-image in that spirit. I haven't been talking enough about community stuff. I used to call it education and outreach, but that seems really, really wrong. What it's really about is community. 'Cause it's not just like you want to, shout, outreach, outreach. You want to interact. You want to go back and forth. So I've been gradually talking to more folks and starting to work with folks. Lou Wilson and I actually made a collaboration, and we submitted this paper to a crazy workshop conference in computers called Dialogues in Natural Code, and I talked about that in the last update. And the news for this update is it was accepted. Actually, it was conditionally accepted. So one of the reviewers, of course, had problems. Didn't really, even the negative review wasn't that horrible, but they wanted some changes, and so we're working on that, and the changes are going to have to go in and get accepted or rejected before the next T2sday update. So that's part of our goals. But what is Dialogues on Natural Code about? Well, it's about, talking in terms of people as if people are programmers. People are and people are computers. So we're programming each other by doing these acts of code transmission like I'm doing right now. And that the idea of the self-image and this strange looking symbol that looks like a little guy or whatever it is called the self-image. And that comes from a separate crazy endeavor that I've been working on a long time, actually longer than the T2 Tile project by a lot, but it's going very slowly, called the Hyperspace Academy, where the goal is, as far as anything, is to collect all the materials, make a curriculum for how to understand us as living computations and how to make sense out of things without using all the sort of crazy, well, that's just human nature. Nah, it's not human nature. It's the nature of computations. The Hyperspace Academy, in principle, is trying to gather that information, organize it, create it. So, the self-image, the key to it is that instead of being any specific thing, instead of saying, I think, therefore I am, so the fact that I'm a thinker is the important thing. What we have, the self-image consists of 4 processes. So we are a collection of processes rather than a specific thing. Is this, is that. The 4 processes: input, sequence, judge, and output. And, input, sequence, and output are very familiar from digital computing. Judge is a little bit weirder, but the claim is that all 4 of them typically have roles in significant, important computations that we would want to understand. So, from the paper that Lou and I made, this is a kind of a goofy little data sheet explaining the self-image API. I'm trying to call it APIs instead of APIs to be the technical term for natural code. API is an API, so self is an API. And so the point of this little symbol is that you got input is in there, output is in there, sequence goes around the head, and judge goes up and down the feet like that. And we try to analyze stuff, and in particular, we can implement machinery based on this stuff, and that's what this project is about. So the goal is in 2024, which feels very quick, implement all 4 self-image processes on the T2 matrix, improving BV's ability somehow by virtue of having all 4 of them. Now, at the moment, BV clearly has a notion of input and output that comes from the sensors, that come from the simulated, the 3D environment, the physics environment that we're using, PyBullet, and sends it up to what either the matrix itself in the other room or the simulator, the MFMS simulator, if I'm just debugging stuff. But it really has not, and it doesn't really have a sense of sequence yet, or has a very, very limited one, and it has no really sense of judge. The next goal is to try to get it to do some kind of sequence. In order to do that, I decided I needed to step back and change a whole lot of stuff. So it's really hard to see what's going on here. This is all fuzzy, but the little teeny white dots that you see there that make kind of a sort of a mushroom shape with a little stem down it, those are actually the sensors and the motor terminals where information comes from the spine and goes back to drive the motors. And these larger things in between are the signals that are moving from one to the other. And the reason it's in the shape of a mushroom is so that all of the signals can kind of shoot through and see each other and get from A to B without running into a lot of trouble. So the point was to get it close together. But this has the significant limitation that every single site in the grid, which we can hardly see in this picture, it's so zoomed in, has to have room inside it for all possible destinations. And so there were only 4 destinations that we had in BV's original brain, so we could fit it in. But if we want to have a lot more destinations, we're not going to be able to do it, so we needed to reinvent it. And the idea was to go with crossbars or something like crossbars. Now, crossbars comes out of, well, it was most useful in telephony when you want to pick up a phone and dial a number and talk to somebody somewhere else. And in the simplest version of it, you could have, all the incoming lines coming down vertically, say, and all the outgoing lines moving out horizontally or vice versa. And by putting plugs in, making connections at various cross points, you make connections. You make wire connections. Now, this is the simplest thing, and there's lots of other ways to do it and lots of super refinements and so on and so forth. But just to take the simplest idea. So, over the last month, I have implemented XBAR space 2D, which is this simple little so we have a grid. We have a 3x3 spaced grid, and each element of that grid is XBAR space 2D is capable of representing a destination on a column or a destination, a source on a column and a destination on a row, and to be able to have one outgoing signal heading down a column and one incoming signal heading across a row. So unlike the real crossbar, the official crossbars in telephony back in the day, where when you made a connection, you actually made copper connection. It was actually an electrical circuit from here to San Francisco if I'm calling long distance. And that is, incredibly expensive, but also really great for latency, which was the sad state of talking to people on the internet today, the horrible latency. It's because we don't have this kind of switching anymore. In this case, it's not circuit switching. In this case, each individual atom is forwarding the signals through as it comes along. So it's not going any faster, but it has a pre-reserved space for outgoing and incoming signals. Okay, so here's what it looks like now. I think I'm already running way late, but we'll go along today because I messed up at the beginning. So here along the top row are the sensor inputs, and here down the left-hand column are the motor outputs. And as the thing runs, signals come in and they switch and go over to the other side and so on. So let's take a look at how that's coming along. So the architect came down to the lab to talk to BV and said, "We want to give you a self-image." And BV said, "Cool." And the architect said, "So is it okay if we replace your brain?" And BV asked, "Will it make me smart?" And the architect said, "Well, we're not sure, but we know you'll have a self-image, though." And BV said, "Okay," and so the work began. For a long time, BV just sat there as bits of brain flickered in and out of existence. But finally, BV began to move, and it was clear that BV's new brain was not very smart at all. But the engineers kept working, and gradually things began to work, very, very gradually. The first task was pursuing yellow balls, and BV was eventually able to do that, although the follow-through had problems. After all, Red Escape was an entirely separate grip that BV's new brain didn't have. But even after the Red Escape began functioning again, there was still tricky adjustments that needed to be made. And then, of course, there was no Explore. So after BV drove the yellow ball off, BV just sat there. During the tuning of the red sensitivity, sometimes BV was so touchy about red that BV backed away too soon and didn't even drive the yellow ball into the void. Still in all, eventually, BV's 3 grips all began to work again. They didn't really work much better than they had before, they did work quite similarly to what they had before, all the way down to the very slow approach when BV was pursuing a yellow ball from far away. There was something different. Something had changed in BV's eyes. BV's new brain could move BV's eyes. It didn't really know what to do with it yet. That was for the future. So BV's eyes are two more motors to rotate the left and right eye stalks, that's what I call them, and that creates a lot of trouble. And at the moment, BV's brain is not complex enough to do the calculations that I would like to do to get that information to be used more sensibly. So that's the current state of things. We were supposed to have crossbar spikes, got that. Body affected display. I'm not even sure what that means exactly, not so well. But next up, August 6th, demo the crossbar sequencer and so on. We shall see. Basically, what I need to do now is step back and clean up the crossbar stuff that I have, generalize it a little bit so that it can go in different orientations and stuff like that, so that we can start sticking multiple crossbars together to make more complex switching architectures. That is it. The goals for next time, officially, the Onward Essay Revisions. That's the paper with Lou Wilson and I have to be submitted. BV recalls a sequence, the third process of the self-image, and have a whole bunch of fun. One of these days I'll stop screwing these things up. Thanks so much for being here. I hope to see you next time. Oi. Okay. Let's go say hi in the chat. Okay. Hey, wow, 8 folks. Anywho, actually, one of the things that I wanted to do, but I ran out of time because the timer was now blown since I restarted, but I didn't restart the timer. Hey, Schlabberman, good to see you. That looks like a cat in a box. That's a good thing. I like cats in boxes. So one of the things I was going to do was show. Thank you, Alex. I don't have I need to have a thing that puts the chat up into the screen so that people can see their own words, right? I tried to work on one of those, but I hadn't actually got it reliable enough or working enough. So Melon from the Void, very interesting stream. Thank you. It's really hard to strike a balance between, completely nerding out and explaining, what at concrete means on the whole YouTube is complaining about the bitrate on the thing, and please stop. Anyway, so actually, maybe we could just take a look at what I was going to show. It was just this. So this is the second of BV's adventures that we saw. Is actually this simulation that I paused because I was trying to keep the stupid CPU fans from coming on. But we can see, so in particular, you can see what the crossbar looks like with the signals coming in from the top, going down, and then going which way? I can never get these things straight. This way, I guess it would be screen right, left. But the point is, you can see the sort of crossbar nature. You can see that actually the grip is changing now. It used to be a yellow, which is pursue, and now it's changing back and forth between yellow and blue, which is explore. And the reason it's doing that is because down here, if you see this hist picks business, where is it? I can't find my hand. Somewhere down here where it says hist picks, and it's got a bunch of numbers there. The first three numbers are the left yellow, and the second three numbers are the left red. In the second row, it's the same for the right sensor. And when those numbers start getting small, like those are pretty small, when BV is actually handling a ball, the first yellow numbers are up in the hundreds and stuff, and those are the same numbers that you can actually see in the little BV's eye boxes in the plain display. But the point is, this is now going at brain speed. If we were to look at the BV snapshots that are being collected, BV would be like a tree growing. All of this stuff would be going on, and at our time scales, we would say. This is a still frame. So it's kind of interesting. You may occasionally, every so often, see a white little circle moving along the top row. That's actually a signal that's going from the corner, the upper left corner, which is the grip, the thing that decides, should we pursue, should we avoid, should we explore. When it changes the grip, it needs to send it to the center of the whole diamond. So it does that by sending a little signal packet, a single atom that hill climbs to the root and says time to change. That introduces a little bit more delay in the grip changing. But as far as I can tell, it's really very interesting because since we're not deterministic, there's no way in hell that this brain reimplementation is going to work identically to the mushroom dome of the previous implementation, because even two different runs of the mushroom dome don't work exactly the same. And when the stuff that's running on the actual matrix, there's code that tries to find the center of the tile to get the fast events and stuff like that, so that all the stuff in the mushroom will be able to communicate, but it's approximate, and so sometimes a little bit off the right is off in the slightly slower space, or the left, or is off in the slightly slower space, depending on where the root gets plopped down, and that makes that BV acts a little different than the other BVs like that, and that's table stakes, right? That's par for the course. That's what we should be expecting for non-deterministic, robust first, where the whole point is that at every level, as much as we can put in, as much as we can stand and afford, we're going to handle variation and keep on going. So that doesn't mean that the variation is eliminated and you then have determinism from then up. It means that the systems can keep on going. They reduce the uncertainty enough that the next level can reduce the uncertainty more and keep on going, and so on and so forth. So the fact that, one of them might have a sensor that's in slightly slower space than another BV means it'll act slightly differently. Will that be that, the beginning and ending of the whole thing? Will that other BV be completely unviable? Well, it's possible. It might be. But all this stuff all has some smoothness. It all has some redundancy. It all has some sort of linearity over space. And so anyway, that's just another example, a typical example of how doing this work, trying all this stuff out and just seeing how it works. And, so again, this is the world's stupidest manual crossbar in terms of its architecture, and it's not very affordable. You can't really scale it up because you've got a column for every sensor, you've got a row for every motor, and so you have the product of those for you add more motors and more sensors, the whole thing goes up quadratically. So telephone network exchange has a very well developed set of body of knowledge about how to engineer multi-level crossbars and all this stuff with all kinds of tricks and so forth to make what is now dying art, the dinosaur of circuit switching, rather than packet switching, so that when you make a phone call, you actually essentially have a connection, a piece of wire all the way from your mouthpiece to the neighbors, the faraway persons. Now, the long distance stuff, and now almost everything goes by getting converted to digital and going over digital. But at the very least, when you pick up a hard line and dial a number, you can be guaranteed to have pretty low latency and pretty low jitter, which that's what made fax machines possible. That's what made modems possible, was the fact that a circuit switch, the telephone network, was as good as a piece of copper going from one to the other. So you could really count on the timing. If you sent a bit through a millisecond after a previous bit, it will arrive a millisecond after the previous bit with pretty good accuracy and so on. Anyway, so this is what it looks to me like. Oh, and then again, probably can't see it. Let me use the mouse. Over here inside the grip, there are these two M-Fix call valves, a little array. That's a running fixed point integration of how much yellow in 0 or red in array index 1 that BV has experienced. So the signals that you see that are getting shot along the top here are ones that are destined for the grip. And one of the features of this crossbar is that it can send a single signal to multiple destinations. As it moves down the column, it can spit off one onto that destination, move on to the next destination, and so on. So, and in fact, it's even doing computation at the cross points. When a signal moves from being an outgoing signal from a sensor to an incoming signal being a motor, there's code that runs that depends on both the source signal and destination motor, so that it can map values. For example, right and left motors, and in one case the sign has to be changed, things can be rescaled, and so on. So even this very simple crossbar actually has quite a bit of programmability, and the signals actually move through the grid. That means the rest of the 3x3, we turn the grid lines on here. So, once again, this is, so all those X2s are those crossbar space points that we have. These STs and stuff up here are the sensor taps that are getting info from the physics engine and sending signals down, which are then moving in and so on. So all of the space in between these things, these little 2x2s and the little pockets, again, this is HC3, so it's 89% nothing. That stuff is available. That space is available. And my plan is that this hard-coded switching that we're doing now, based on hard-coded grips, is going to be the base level, the evolutionarily supplied behavior dynamics, and then we're going to try to figure out ways to infiltrate other atoms in there that have programmed information. And each of the X2s, when it's doing a switching operation, it'll look to see, is there a current program here that wants to modify how my switching operation is supposed to happen? If so, delegate to that little bit and let it do it. If not, fall back to the basic thing. And that's going to be the way we're going to try to subsume the low-level pursue, escape, pursue, avoid, explore of the basic grips. So that's the plan. it's all going so slow, but we'll see. Not dead yet. So that's that. Let me go back to see what we have here. Alan, hi. And I think BV is very cool too. Hey David, glad you made it. And Tiggs, great. I'm glad you're here too. Steiner Systems, mathematics. See now, David, I know virtually nothing about the mathematics of crossbars, except that if you can take advantage of the property that there's always one input to go to one output, everything becomes easier. And of course, I've already abandoned that by having the multiple delivery possibility. But again, rather than saying we should do math and traditional algorithmic analysis to allow us to make bigger crossbars, the goal here is to say, okay, the natural size of these things wants to be like blah, so how can we use multiple crossbars in a way that's flexible and programmable and so forth, rather than just saying the goal is to get bigger and bigger and bigger and still just be a crossbar. So we'll see. Software FPGA, well, all of this stuff, because it's spatially distributed, has FPGA flavor, or has chip flavor, for that matter, because, of course, chips are actually laid out in space. One has to care about distances between computational elements on the face of the chip, and logic elements and distance in FPGAs for clock tolerances and all of that stuff. So there is an absolute sense in which, only because the T2 tiles are so much bigger, so that you'd take, 1,000 of these things, or 100 by 100, whatever, 10,000 of them, and that would be sort of the equivalent level of spatial analysis that a typical, some kind of typical FPGA these days, which, spans an incredible number of levels, orders of magnitude, depending on how big your pockets are. Anyway, so we'll see. And I do think, this is all secret, right? This is off the record, just between us. I do still think about T3 tiles, and I do still think about FPGAs as an essential component of the T3 tile. And, FPGAs, their price performance is getting better slowly. They're still this kind of niche product, so they tend to, add 1 million gates, add 1 million more logic elements, and double the price, and so on. But they're getting to the point. I saw a piece of, I can't remember the name of it, a DIY thing that has a pretty powerful ARM sock on it, and 100,000, 200,000 logic elements, which is tight, but it also has, 32, 64 block RAMs or something like that. So I do think about playing with FPGAs to prototype T3s and doing a much lower focused thing, where it would be, how fast can we make one event window go? And we do a whole lot of re-engineering around the limitations of FPGAs. In particular, the fact that, we currently, since each event is sequential code, in order to do a single event, in addition to what you think of, the cellular automata space, we need the code. We need to get the code. The code has to reach the processor somehow. And so where's the code stored? And if the code is stored in DRAM, then what if somebody else is looking for a different bit, because different sites are working on different elements which use different code? And so the fantasy would be to make an entire Ulam physics that would fit somehow in one block RAM. And get, or a couple of them, a couple of local ones, whatever it needs to be, the granularity. So there would still be enough block RAM to have a local stack and scratch space and all the other stuff that it would need, plus the code that would represent it. So each of these pairs of block RAMs, or whatever the heck it is, little colonies of block RAMs, would have a complete copy of the physics and the events that are happening all over the surface of the FPGA would only have to fetch the instructions from the nearest block RAM colony, and would avoid contention at a common RAM, DDR6 or whatever the heck it is. Mead and Conway, and so Lynn Conway just died in the last month or so. Anyway, and all the stuff that I have done, the limited stuff that I have done with FPGAs has all been, using the standard cells, standard logic elements. Anyway, well, so that was fun. And folks, we're getting close to double digit folks coming to the live stream. I appreciate it tremendously. As I was saying, I think I said this was messed up so much as usual. It's about community. It really is about community. And when I used to talk about the Department of Education and Outreach, because I was one of the pretenses that I used to play with. I don't do it so much anymore, although it's all still valid. It's all still canon. It could be brought back to life anytime one wants to. Education and outreach it's got this real one-way attitude to it. It's got, it's to give information out, to reach out for people and stuff like that. To what? Reach out and give them education and then send them on their way. And yeah, that's really important. But a much better way to think about it is to find good-spirited, like-minded folks and say, let's talk to each other. Let's get together and do all kinds of different things. Do your stuff, do my stuff. I'll come to your stuff because like-minded, good-spirited folks. So anyway, if silicon reached the point that you could just print a magic chip just how you wanted it and have a little array of little standards that could talk to their neighbors and run up, do you think it could be programmable or necessitate a fixed laws of physics? I think it could absolutely be programmable. I mean, if we're talking about doing an ASIC or something, and Intel gives me, $10 million or, 5 engineers, so on and so forth, magic, all that magic stuff, I think... and a typical example is the Grayskull thing, 96 processors on a chip. I've been leaning away from that design at the moment because they don't really have enough RAM, enough local RAM. And they do have an instruction cache. The instruction cache has to get loaded by hitting DRAM that is not 96 ported, so there's contention at the DRAM if you're looking for different pieces of code because you're running different events all over the place. But if you could manage to make it so that, virtually all the time you'd hit in the instruction cache, then that might be okay. And what I would much rather have some kind of bigger local instruction memory that, again, if I was designing the chip and I didn't have the movable feast background, there's no way I would spring that much area for, local instruction memory. But again, I can't figure out from the Grayskull specs how big the instruction cache is on each of the 96 tiles, and that makes a big difference, right? I mean, if we could make a virtual machine that would execute bytecodes out of local RAM and get the entire virtual machine, like a fourth machine or something like that, to fit in the instruction cache, so it would only have to fault in essentially once for each of the 96 processors, and then it could do bytecode interpretation using the code being in local data store, then, we could be cooking like that. It's a big task, and so we'll see. But yeah, and I get, the bigger picture is I'm not sure I have the strength to do a whole another start like that. I've done a little bit of FPGA stuff, so I have a sense of the hinterlands, and it would be fun. It would be a whole lot of learning curve stuff, and the goal would be to say, unlike the T2 tile, where the goal is to just get flexibility so we can see what we want, the goal of this T3 prototyping experiment would be to make a limited complexity elements where the sequential code that defines an element could only be so big, or the stack space available for calling functions can only be so deep, whatever it is. But try to get it to, run like a bat out of hell, and see if we could approach, 10 milliaire, 100 milliaire, who knows. Anyway, that is all for fantasy. And again, I spend more and more time thinking I should be writing natural code, not VHDL. Or Ulam or Rust or whatever for that matter. So we'll see. Thanks so much, folks, for showing up. I'm getting hot here. I need to turn the air conditioning on. And I guess I will get the some kind of interaction combinator element. That sounds like functional programming. Which I don't know well, but am predisposed to be grumpy about because they try to hide state, and I don't think one should hide state. I mean, a lot of functional programming stuff is really, really beautiful. I admit it, but anyway, okay. I guess, have I responded to most of the stuff that people have talked about? Alex, Kim, Alan. I guess that's about it. Okay. Well, again, folks, thanks for stopping in. Cutting time out of your day to actually be, only 20-second latency or something like that. I want to experiment with other communication protocols as well. This is something that I think about a lot, probably more than I think about the T3s, to be honest. Anyway, okay, I'm going to call it, and I will see you folks in the Discord if you are there. I'm also on the Fediverse and sending more stuff. Robust levels of complexity. I'm not exactly sure what you're getting at there, David. Certainly, one of the slogans is structure at all scales. And so we are rejecting the idea that, you can just have CPU that goes faster and RAM that gets bigger, and that's all you need. You don't need any structure between 1 byte and 1 terabyte. And of course, when you look at actual systems, there is all this kind of structure, but the hardware makes the pretense that there really isn't. And so the further claim in indefinite scalability is that you will need, just as you will have structure at all scales, you will need robustness at all scales as well. So you take care of the errors that are kind of local to the space-time window that you are at, and then you provide stuff up to the bigger, slower stuff that you are part of, and you try to give better than you get. That's the fundamental principle of robust computing. It is, you cannot guarantee it's perfect, but you try to give better than you get. And if everybody does that, then the system will have a pretty good chance of limping along if there's a way that it can figure out to do it. And then the rest of it is mostly springing the bear traps of the fatal flaws, the single point failures that one may not have predicted at all before putting the system together and starting to study it. I'm getting at robust levels of complexity with your stuff. Well, I mean, I'm trying. I am trying. I have trouble with complexity because it's kind of like one of those words that's defined by what it isn't, like that. But to the degree that there's a relatively clear notion of complexity, then okay, sure. I'll just call it structure. Like that. All right. And okay, I'm gonna go. Still got 7 people. Well, I guess the chat still works for a little while. I don't know what it is. Well, tell you what. I'm gonna mute it and turn on the AC. Nah, I think we're done. Let's call it. Let's be a happy winner. So okay. All right. Okay, folks.